Horti-BlueC is funded by the European Regional Development Fund under the Interreg 2 Seas programme. Horti-BlueC aims to create a more sustainable, circular and soilless horticultural process.
A lot of people don't really know how or where their food comes from, and well, they can't keep cows and pigs, they will grow plants in their back gardens, but they may not realise that what we do industrially is still miles apart from what they do in their own garden. So actually talking about how we can create the environment that the plant needs to get the most out of it, and how we can do that in an environmentally friendly way as possible.
So in greenhouses, for instance, growing media allow to use nutrients and water in a very efficient way. However, we try to increase the sustainability of the growing media by replacing peat, coir or mineral wool by sustainable local materials like compost, wood fiber, biochar or chitin.
Normally, tomatoes are grown in this unsustainable growing medium, and then we go to this magic mix of sustainable materials, and we saw that we had similar yields. So in fact, it means that you can have similar yields of your tomato, but with a more sustainable growing medium.
It's an interactive VR experience that leads them through the process of recycling material into growing media and then seeing how that impacts the growth of a plant.
This demonstration is essentially comparing the different levels of antioxidants in different types of tomatoes from the Isle of Wight.
The darker the color, the more antioxidant you have. So Piccolo has more antioxidants compared to different varieties of tomatoes.
I've been working with tomatoes and tomato products for quite a while, and I've got interest in their antioxidant and anti-cancer properties. So today in my presentation I've shared some of the work that we have done in with regards to their anti-cancer properties.
Consumers declare that they want to be more sustainable, but they are not actually doing it. So there is this attitude-behavior gap. But this is because there are so many barriers to sustainability, like price or awareness or life beliefs. So companies should help us in understanding more about sustainability and help us to overcome such barriers. So maybe with this collective effort we can be more sustainable for real.
So, welcome everyone, and this is the final Horti-BlueC webinar actually, and it's going to be focusing on life cycle analysis of biochar in new growing media blends for strawberry and tomato. Briefly, Horti-BlueC is a multi-partner project supported by the European Regional Development Fund via the Interreg 2 Seas programme. Horti-BlueC is developing, in short, a sustainable greenhouse model for commercial horticulture. Just want to cover a little bit of housekeeping. We're recording the webinar and we will be posting it on our YouTube channel. So if you don't want your image to be recorded, please turn your cameras off. Please keep yourself muted throughout the webinar. Look out for some polls that will be coming up. The answers to the polls are anonymous, so don't be worried about choosing the wrong answer. And there'll be a Q&A after today's presentations. So please post your questions into the chat box. I noticed there's a Q&A box as well. So will we be using that? Bart, will we be using the Q&A box too?
Yeah, please put your questions just in the chat that we can see it, yeah.
Okay. So we're going to hear presentations from our project partners TNO Energy Transition, and they're an innovation organisation in the Netherlands who carry out applied scientific research. And we're also going to hear from the project lead, Dr. Bart van der Kasteel from ILVO, the Flanders Research Institute for Agriculture, Fisheries and Food. So let's begin now with a brief introduction to the project and today's session from Bart.
Thank you, Cressida. So we are now at the final webinar of Horti-BlueC. The 4 previous webinars you can see here. So there was one on large-scale gasification.
There was one on chitin production, there was one on spent growing media, and there was one on new growing media blends. And all information you can find here and on the website. And the presentations of today's webinar will also be available on the website directly after this webinar. So we have now a webinar on LCA, and it's strongly related to the content of webinar 1. In webinar 1, we had like also a cost calculation of biochar production. And in webinar 4, we focused on how to make new growing media blends especially for strawberry and tomato cultivation. Biochar has been a theme and several activities of Horti-BlueC. Of course, we started with producing biochar in combination with energy production, and this energy is aimed at to be used in greenhouses. And the next step, we used biochar in growing media in 2 ways. And the first way, it was to use it in small amounts. So we talk about grams per liter, and it was in terms of increasing disease suppression, or to use it as a fertilizer or as a liming agent. On the other hand, we also used biochar as a bulk replacement, so in larger volume percentages in the growing media. At the end of growing strawberries and tomatoes, we have spent growing media, and we also try to upcycle them as biochar. So it was also used as feedstock for biochar production. And also the spent growing media with biochar, we can use them for additional carbon storage in agricultural fields. So that was also a theme in the project. So the 3 topics that we will further discuss today are here marked with the green arrows. And this is actually the scenario. So we will combine gasification with CO2 reduction and with biochar production. And this scenario is based on actually replacing natural gas. So in the baseline scenario, we heat greenhouses with natural gas, while in the new scenario, we have the gasification installation that allows us to produce energy and biochar. And this energy production, it's really the source of revenues for the whole production process. So the energy can be used for lighting or for heating. And for having this energy production, we need optimal feedstocks like woody biomass or miscanthus or flax chives. And the biochar that is produced, we can use for bulk replacement in growing media. And when we started the project, there was already a pressure of replacing natural gas by renewable gas. And I think today it's even more actual. So we think that this concept can be implemented in the project area in 5 years from now. So when we convert, for instance, flax chives into biochar, as you can see here in the picture, there are some things to take into account. So whenever you talk about growing media, please express the amounts in volumes, so as cubic meters or liters, but not as a mass, because growing media, it's always expressed as a volume. Before we used the biochar into the growing media, we always put water to it to avoid dust formation. So we added an equal amount of water as the dry matter biomass of the biochar applied. And we know that biochar is more expensive than, for instance, peat. It's like 2 to 5 times more expensive for the same volume of material. On the other hand, we have to take into account that we have revenues from energy production, as was highlighted in the first webinar. You can maybe use the biochar for more than one cultivation, so it's a growing medium that can be used more than once. And in the end, you have a very stable carbon form, so maybe this carbon can give some carbon credits, so an additional revenues for the system. However, there are also some pitfalls when we talk about replacement of the currently used materials in growing media. So there is the question of sustainability of materials, but an evenly more important question is the availability of these materials in terms of amounts and also in terms of quality. And of course, it's always better to work with renewable materials, so we have to also take it into account. And very important is, of course, that growers should be able to switch to alternatives in a very short period of time. So we should be ready to use these alternatives, whatever happens the coming months or years. We should have alternatives that work already. So this was the introduction, and we will now move to the LCA results that will be presented by TNO.
Thank you, Bart. So now I'd like to introduce our two speakers today, both from TNO Energy Transitions, and they are Maria Saric and Heather Ray. So Maria is a chemical process engineer specialising in design, evaluation and life cycle analysis of energy conversion processes. She's a master's degree in chemical engineering and has worked at TNO since 2007. She's worked on national and EU projects and has been involved in the design and testing of membranes, membrane reactors and heat integration distillation columns. Heather is a scientist focusing on processes and technologies for upgrading biomass residues to produce energy as well as other valuable products. She completed her PhD in environmental engineering and has also completed life cycle analysis training. In addition to her work as a scientist, she is also a project coordinator at TNO for internal and EU projects. So over to you.
Thank you. So we'll present, as we said, the results of the life cycle assessment that we did for the production of tomatoes and strawberries. And first, I'll give a bit of an overview on our approach. I'll discuss the results for strawberries, and then Maria will go through the results for the tomato production. So just to give a bit of background here and the motivation for this and any life cycle assessment, it's really to look at environmental impacts. So greenhouse horticulture has quite an environmental burden, including natural gas for heating, electricity for lighting, and conventional substrates like peat and stone wool. So there's a real drive to make greenhouse systems more sustainable and lower their environmental impact. And so, of course, one of the ways that we're proposing this is through the use of more sustainable substrates. So the goal of the life cycle assessment was really to evaluate the environmental impacts of conventional and proposed alternative substrates and blends of substrates. And really with the goal of highlighting options towards more sustainable greenhouse systems. And just up front, I want to highlight that a life cycle assessment really only gives information about the environmental impacts. We're not considering any economics in this type of analysis. And our accuracy is only as good as the data that you put into the life cycle assessment. So we follow ISO standards and use EU approved databases in our analysis. Also, the impact of biochar on the quality of the soil or plant growth beyond carbon storage is not considered because the data just simply isn't available yet. So for our life cycle assessment, we really focus on the production of tomatoes and strawberries. We use data directly from growers, and of course we checked with them and with the partners as well to make sure that the data made sense. And we assess the global warming impact in units of CO2 equivalents, and also a bit of a damage assessment that looks at the impacts broadly on human health, ecosystems, and resources. Our functional unit is 1 kilogram of tomatoes or strawberry produced. So we look at the impacts per kilogram of tomato or per kilogram of strawberry. We use the SEMAPro software and database. We use EcoInvent, and we use, also, of course, as I said, data from the growers. So of the substrates we considered, the pure materials that we considered were peat, biochar, and here we considered 2 different feedstocks for biochar and 2 different production methods. So actually there's 4 different types of biochar. A wood fiber from forest residues, and then conventional stone wool substrate. When we considered blends, we used peat as the main sort of blending material. So peat with biochar, peat with wood fiber, a blend of the 3 of those. And we didn't consider stone wool in substrate blends because it's not, you're not really able to blend it in its form. And based on previous research that has been done, we did a maximum of 50% biochar in any given blend. So this gives an overview of the system boundaries for the more conventional substrates. So the substrate is produced, and then it's packaged, and then it's shipped to the greenhouse, which is where we really see more of our inputs and outputs to the system. So we look at how much electricity for lighting, heat for the greenhouse, the addition of water, nutrients, fertilizers, and then what happens to the substrate when it's done or when it's spent. What are the emissions coming out of the greenhouse? And then of course, what's the yield of the product? For biochar, it's a little bit more complex. So again, I said we considered two feedstocks. So one is miscanthus. So we also consider the impacts of growing and harvesting the miscanthus, or park residues. So also the collection of the park residues. And by park residues, we're really talking about woody material that's chipped. And then that material is transported to the greenhouse site, and we're assuming that the biochar production system is on the same site as the greenhouse. And in this way, we can use heat from the biochar production to heat the greenhouse. We also assume a certain scale. So we produce a certain amount of biochar, and we only use part of it for the blends, and the rest might be excess that would have another use. But we're always producing the same sort of quantity of biochar. And then of course, in the greenhouse, you have similar inputs like electricity, heat from the biochar, electricity, water, nutrients, things like that. So as we mentioned, we have two different methods of producing biochar that we considered, and they're called ENERCHAR and PYROCHAR. And you can look here at the differences between them, but the key takeaway here is that ENERCHAR produces more energy and less biochar per same input of feed. But the stability of the biochar that's produced with ENERCHAR is better, or is longer, so it'll survive in the soil longer, better carbon sequestration than that of the PYROCHAR. And if you look at the anticipated price per ton, you can see there's quite a range. And that price depends a bit on feedstock, but it really depends a lot on the scale. So an ENERCHAR installation could be at a much bigger scale. The PYROCHAR installations will likely be at a smaller scale. So that's why we would expect a higher price per ton. But the quality of all of it is very good. These are the different blends that we considered in our model. So we have the 100% of the sort of pure materials, peat, stone wool, biochar, and then blends different ratios of peat and biochar, peat and wood fiber, or all three together. We received a lot of data from the growers, and so we're considering a cherry tomato produced in a heated, lighted greenhouse, a cherry tomato produced in a polytunnel, so no heat or light added, and then strawberry in a greenhouse that's heated but no light. And so that's used under those conditions. We received data on the yield, the volume of substrate, typical cultivation cycles in a year, the heat use, electricity use. So this is all measured data, water use. We received very detailed fertilizer inputs, which are in the model, but here I've just sort of lumped it all together. And the yields, we are assuming are the same, no matter what substrate or blend of substrate you're using. And that was already confirmed in greenhouse trials. So we're confident in that assumption here. So before I move to the results, we have our first poll question, which is for strawberry production. And this is on a reference case of 100% peat as a substrate, again, in that greenhouse that is heated but not lighted. So which input do you think has the highest environmental impact on the strawberry production? So heat, the substrate, the fertilizers, the pesticides, or the water used. So, okay, I see some results. So most people think, well, it's quite a range. So pesticides, very few people. Most people think it's the heat, 36%, but quite a lot of people also think the substrate has a big impact, and water and fertilizers as well. Very interesting. Okay. So here come the answers. So it is indeed the heat that has the greatest impact, by quite a lot actually. So again, reference case. In total, we calculated about 5 kilograms of CO2 equivalents per kilogram of strawberries produced in this scenario. And of that, the heat is responsible for 71% of those impacts. And the peat substrate contributes 15% of the impact. So this is a summary of the impacts for those pure materials. Now you'll see that stone wool is included here. And even though stone wool is not a typical substrate for strawberry, it's sort of a theoretical case and it's in the model. So we tend to use all of the pure materials for every calculation that we do. And it gives a bit of a comparison as well. So this is the impact in terms of CO2 equivalents per kilogram of strawberries produced. So the reference case with the peat substrate has by far the highest impact. And when you look at the biochars, you see quite a reduction in the impact. And again, this makes sense because we saw heat was quite impactful. And so if you're using the heat from your biochar production to heat the greenhouse, you're going to remove those impacts. You also see a decrease with ENERCHAR compared to PYROCHAR, and this is related to that stability of the biochar and the carbon sequestration with the spent substrate. If we look at blends, we see a similar trend. Adding a bit of wood fiber to the peat does decrease the impact a bit. But again, you really only see those significant decreases in the impacts in terms of CO2 equivalents when you're adding biochar into your substrate, into your blend. And here for this, the biochar we assumed was sort of the best case from before. So it's from park residues made with the ENERCHAR process. So in these, from these blends that we looked at, the best case scenario that we evaluated was a 50-50 mixture of peat and biochar. This slide just gives, it's the same information, but it gives a bit of a breakdown of the different components. So you can see really here the impact of the heat in the non-biochar scenarios versus when you use biochar. And you can also see the impact of the substrate in particular, where the emissions are negative, below zero there for the biochar, where the biochar is added to the soil. So in this case, as before, I mean, the best scenario is the biochar substrate. In a blend with peat is the best sort of blend scenario. As I said, we also did a bit of a damage assessment. So the way this works is the condition that has the highest impacts is assigned a value of 100%, and then the impacts of the other categories are relative to that. So in terms of strawberry production, a peat substrate has the highest impacts with respect to human health, ecosystem, and resource use. And then that's followed, it's very similar in terms of impacts for a mixture of peat and wood fiber. But then again, those biochar blends, this is where you see quite a reduction. And again, that's related to the use of heat from the biochar production to heat the greenhouse, and also this carbon storage. So that is it for the strawberry production. And so I'm going to pass it over to Maria, And yeah, knowing what you know about strawberries, we have our next poll question.
Good afternoon, everybody. So we have a next poll question on the production of cherry tomatoes in lighted and heated greenhouses on the 100% stone wool substrate. And the question is a bit similar to the strawberries. If you can assign the let's say the factor that could have a highest impact. So is it heat, electricity, substrate, fertilizer, pesticides, or water? Okay, quite interesting. So the heat is voted as the highest impact, followed by electricity and the stone wool substrate, and water a bit less, only 3%. So let's move to the results of the calculations. So what we see here is that heat has high impact, but actually the highest impact comes from electricity use with 57%. Heat is 41%, and substrate is less than 1%. And actually, the total CO2 equivalent per kilogram of tomato calculated is 12.8. Which is because of this electricity use higher than in the case for strawberries. So if we move further, here you can see also the same type of graph like my colleague presented, only for tomatoes. So it's a kilogram of CO2 equivalent per kilogram of tomato. We already also placed this pure material, you can see peat. But because peat is typically used in these alternative substrates in the blends, so what you can see is that peat has the highest CO2 equivalent emissions per kilogram of tomatoes, followed by stone wool substrate, and then it is the same, let's say, with the biochar cases, that because of replacement of heat, you will have a reduction of the overall CO2 emissions. So if you look at the substrate blends or blends that we can use, we can see the same trends as for strawberries. So, but we can see with the mixtures with the wood fibers, we have a comparable emissions. And once we move to the biochar blends, because of the replacement of heat, we see the decrease of the overall CO2 emissions. And this is the breakdown of all the impacts. And you can see in yellow, it's electricity, which has the highest contribution. And what is nice is that you can see with in blue, that's an impact of heat, and you can see that for all blends with biochar, this impact is significantly reduced, lowering the overall impact. So it's the same. So we look also for tomatoes on the damage assessment, and we have 3 criteria: health, ecosystem, and resources. They are all relative, so the one for the highest impact is assigned 100%, and they group, let's say, several impacts together. So for instance, for human health, you typically look into the ozone formation, particulate matter, ozone depletion. For the ecosystem, it includes, for instance, land occupation, eutrophication, acidification potential, and the resources, it's depletion of resources like fossil and mineral depletion. What you can see is for stone wool and peat with the wood fiber, for human health, the impact is higher. Where with the mixtures with the biochar, this impact decreases. In the terms of ecosystems, they have a comparable relative impact, and for resources also with the mixtures with biochar, the impact is lower. So now I want to move for, we also evaluate as, let's say, sensitivity study, the cherry tomato grown in polytunnel, so that's without heat and electricity or lightning. So what you can see here, when you reduce that, of course, your overall impact highly reduces from 12.8 to 0.21. So it's a big reduction. And here you can see that most of the impact comes from fertilizer with 54%, followed by substrate and water use. So if you look in the similar graphs with pure materials, we can see that the highest impact is from peat. Peat is this is also can be used later to explain the mixtures. And with actually mixtures, actually pure biochar, you see because biochar has high potential for carbon sequestration when placed in the soil, you can see that you can actually reach even negative emissions. Or yeah, it has high potential for carbon storage. So if we move to the substrate blends, we can see here that compare that, for instance, with the mixture with the peat and biochar, we can, so that's the lowest overall impact. We can decrease for 50% CO2 emissions, so from 0.2 to 0.1. And then we have also the break of the overall impacts. So you can see in green is a substrate, and then you can see that when mixing with the peat and wood fiber, you can decrease the part or contribution from the substrate. And here the lowest one is, what you already saw in the previous graph, is 50% peat and 50% biochar. If we go to the damage assessment, here the picture is a bit different. We can see that on the human health, stone wool and peat mixture with biochar have a highest relative impact compared to the mixtures with wood fiber. Also for ecosystem impact, the peat and biochar have a bit higher impact compared to others. And also for resources, it's the stone wool and peat with biochar. And this is mostly connected to the activities connected to the collection of the, let's say, the biomass, and also processing to produce biochar or the wood fibers. And then we can move to the conclusions. So what we saw from this analysis is for conventional scenarios, most impact is from greenhouse heating and electricity for lighting. There is a large difference in environmental impact between greenhouse and polytunnel production of tomatoes. And conventional substrates, stone wool for tomatoes and peat for strawberries have relatively minor impact compared to the heat and electricity. And for growing conditions without electricity or heat, so that we saw for polytunnel tomatoes, the use of alternative substrates can reduce the impact to almost zero, or even result in negative CO2 emissions. So for alternative substrates, we can say that use of biochar as a substrate or in a substrate blend can significantly reduce environmental impact and associated ecosystem damage due to use of co-produced energy to heat the greenhouse, and also addition of used biochar substrate to the soil can result have a high carbon segregation potential, so it results in negative emissions. The lowest impact is associated with biochar substrate produced with ENERCHAR technology and using park residues as a feedstock. And this can reduce 98% impact for the strawberries case and 40% for the tomato production. So we see that there are still many opportunities for further research. Biochar could play a role in the future carbon credit schemes. Also, there is importance to link, of course, this LCA results with economics. And let's say for future testing, we can look at biochar on a soil fungi growth. So this is already factory that was published from this project, and phytotoxicity and the criteria for testing. And we are open also for further collaboration on these topics. So thank you all for participating.
Thanks both for two really clear presentations. So yeah, very easy to follow. So thanks for that. And now back to Bart.
Okay, thank you. So in this presentation, we will more focus on the interaction of the new growing media blends with fertilizer or with fertilizers, both organic fertilizers or fertigation. Okay, so we can use different types of fertilizers in growing media. So we have the chemical fertilizers or fertigation, which really contain readily available mineral nitrogen, or we can use organic fertilizers or even compost or chitin, which contain organically bound nitrogen, which then and small amount of mineral nitrogen, and this nitrogen should be released by mineralization. And each of these materials might have a different rate of mineralization, so the speed by which the mineral nitrogen is released. So this nitrogen mineralization is actually a microbial process, so we need microbiology to be active for that. But also something else can happen, that mineral nitrogen is actually immobilized from the medium into the materials, and it's then not available anymore for the plant. So that's also a microbial process, so it can happen in plant fibers, for instance. So yeah, we should be aware that when we use materials with a high microbial activity in growing media, it can result in high nitrogen dynamics in either direction. So the big question is, of course, when we move from the conventional growing media to new growing media blends, do we have to change the fertilizer application, or do we have to change the cultivation conditions in terms of fertigation application? So we have a poll for you. So the question is actually, what do you think it's the link between the change in microbial biomass when you add an organic fertilizer to a growing medium? So if this change, how is it related to the mineral nitrogen release? So if you have, do you expect that more nitrogen release is related to a strong increase in microbial biomass, or do you think that there is no link between nitrogen release and the change in microbial biomass? Or do you think it's an inverse relationship between both? So while you still can answer these questions, this poll, we go on with the presentation. And actually here you find some data of typical materials that are currently used in growing media blends like peat and wood fiber, or also some materials that you can use for replacing peat and wood fiber. We have bark compost, green compost, and plant fibers. And well, we see actually that between these different materials, there are differences in, for instance, nitrogen immobilization risk. But we also see very clear differences in the microbial biomass, which is present on these fibers when we express it on an organic matter base. And also when we look at the stability of the material, so in terms of a CO2 release, we see big differences between these materials. So a higher CO2 release means that the material is less stable. So We know that new materials, they contain more microbiology than the conventional materials like peat, but it's not yet clear if it's positive or negative, and we will try to answer this question later on. But first, maybe look at the poll, and most of you think that more nitrogen release is related to a stronger increase in microbial biomass. So I'll answer your question in a minute. Okay, so let's go on. So we did a trial with woody composts, two types of woody composts, which are really very good to be used in growing media blends. And because they were of this high quality, we were even able to use them up to more than up to 40% of on a volume base, which is quite high. And we added also like 30% of peat and also 30% of bar compost. So these were the two first experimental blends, and we compared them, of course, with a peat-based blend, so 100% of peat. And then we had also 3 other blends that we included, that we have included in the comparison. So we had the same blend with the 2 composts, but here we replaced the peat by wood fiber. So we have 100% peat-free blends, and there was also a 5th blend, which was completely free of compost. So it's like a compost-free blend. And for each of these blends, we did tests with effects of organic fertilizers. So we added both blood meal or chitin as an organic fertilizer, and we looked at a mineral nitrogen released during 100 days of incubation at 15 degrees. So here you see the results of this of the total mineral nitrogen content after 100 days. And you see that between the blends there are really big differences, but also between the 2 organic fertilizers. So the statistical comparison was done per fertilizer because there was a very strong interaction. And what you can see that there are actually for the blood meal that we had the highest content in the peat-based blend, while for the chitin used as organic fertilizer, we see that we have the highest content for the 2 blends with the woody compost too. So both the blend with 30% peat, but also with the complete peat-free blend. So very strange results, or very big differences we saw between the blends and between the fertilizers. So with this trial, we tried to see, on the one hand, what is the effect of adding organic fertilizers on the microbial biomass before and after the addition, but also on microbial activity, and that's then in terms of nitrogen release from the fertilizer, but also on CO2 release or the oxygen uptake, so in terms of stability. And here are the main conclusions. So we saw that there were very specific effects for each combination of blend with each combination of organic fertilizer. But in general, we could say that there was more nitrogen release from chitin. And over the 6 different blends, we saw actually that the larger was the increase in microbial biomass in the blend, the lower was the increase in mineral nitrogen concentration. So it's not what we would have expected, but we saw actually like an inverse relationship between the increase in microbial biomass and the mineral nitrogen release. Okay, so we also saw a very positive effect of adding compost in the growing medium blend, as we saw that there was a higher nitrate to ammonium ratio. So it indicates that there is a higher rate of nitrification going on in your blend, which is beneficial for most plants because they can more easily take up nitrate than ammonium. So we saw that new materials, they have a higher microbial biomass, but there was also more interaction with the organic fertilizers. So it's something to take into account. And a very practical advice that we could give is that when you mix organic fertilizers into a growing medium blend, please first let the mineralization process from the organic fertilizer start before you start with growing plants, because if you combine adding the organic fertilizers and planting the plants, the processes are not tuned, and you get maybe nitrogen shortage for your plants in the first days of the trial. So this was the part on the organic fertilizers, and now we move to the fertigation, so the chemical fertilizers. And you may know that we did different full-scale strawberry trials in the Horti-BlueC project. So all blends that we have tested were produced by Aharis, and we had trials at Hoogstraten, at EDAS, at NIAP, and also at ILVO. And here we compared the new blends with peat as a reference or coir as a reference. But today I will show some results from the Proefcentrum Hoogstraten. So they used a gutter system and a double cropping system. So it means that you start cultivating the strawberries at the end of the summer. You have a first picking period before Christmas, and then plants are regrowing in early spring, and you have a second harvest period in April. So here we had the standard fertigation, but we compared the standard fertigation with a reduced fertigation regime. So we reduced all elements to 56% of the total of the 100% fertigation. And we compared a peat-based blend with a peat-reduced blend. And we also had a peat-reduced blend with a small amount of biochar in this test. So here you see the work at the end of the trial. So we took some containers from the greenhouse, and we harvested the above ground biomass, but also the spent growing medium was sampled. So you can see it here. And well, when we look at these two compartments at the end of the cultivation, we know that the above ground biomass, it's highly decomposable, so it can easily decompose. And we had like 150 grams of dry matter per container or per pot, while the brown material, it's the spent growing medium. It's really very stable, although it contains still some plant roots. And it was, and dry matter mass, it was really bigger than the above ground biomass. So we have the green and the brown compartment. But when we then look for one container where the nutrients are found, so you see that, for instance, for nitrogen and calcium, you see that most of the nutrients per container are found in the spent growing medium, while in contrast we see for potassium, for instance, that most of the potassium is still present in the above ground biomass. And then we have for phosphorus, it's not that clear, but it's mostly available also in it's mostly present also in the biomass, while magnesium is then more found in the spent growing medium. But it was for the peat-based blend, so you see it on the left. So you have peat with a little percentage of coir and perlite. But then we had a new blend that we have tested where we have 40% replaced, so by green compost and wood fiber. So we wanted to know whether nutrients would be distributed in another way when we start with this new blend. So at the end, actually, we have the above ground biomass, the green part, we have the brown part, spent growing medium, but we also took into account that you have the initial growing medium, which may also already contain some nutrients. So, and here you see the data for phosphorus on top and potassium below. So when we first look to phosphorus, it's a little bit strange because for the peat-based, you see that the green part is the most important compartment per container. But when you then move to the peat-reduced or the peat-reduced with biochar, you see that the growing medium is then the most important compartment for phosphorus. While on the other hand, you also see that the initial blend of the new growing medium blend already contained much more phosphorus because of, for instance, green compost can already contain a lot of phosphorus. So when you take the balance between the input and the output, you see that they're quite equal. So there is no really buildup of phosphorus, but it's important, an important sink of phosphorus in the cultivation. We see another story for the potassium because in all cases we see that potassium is most available in the green compartment. And also here you see that when you have peat replacement, that you also start with a blend that already contains more potassium. So in a nutshell, we see that nitrogen, calcium, and magnesium, they are most available or most present in the growing medium when you think in the total amount. For phosphorus, it's more or less depending on the blend that you use. And for potassium, we see that the plant compartment is then the most important. So some conclusions about fertigation. Well, one experiment that we also did was on the reduced fertigation, so the 35% reduction in nutrients. And yeah, it was the question was, would it reduce the yield or would it reduce the nutrient left in the spent growing medium? Well, we clearly saw that it mainly reduced the yield already in autumn cultivation, but mainly also in spring cultivation. While on the other hand, there was only a very small reduction in the nutrient export with the spent growing media. So based on that, we could conclude that the fertigation regime used was optimal. It should not be changed because if you reduce it, you have a lower yield, but no smaller losses of nutrients. There was no net effect of the blend on the nutrients in spent growing media. So it means that when you start with a compost in your blend, it starts with higher nutrient concentration, but the same nutrient concentrations are then removed at the end of cultivation. So no net accumulation. And to give you an indication of the amounts of nutrients per hectare of greenhouse that are exported. So we see for the plant biomass, it's mainly the potassium, which is an important source, while for the spent growing medium, it's mainly the nitrogen. For nitrogen, it's important, and phosphorus, it's available. Well, it's equally in both compartments. So this was the part on the fertilizer use and the fertigation. And I now give back the word to Krista for the Q&A section.
Thanks for that, and thanks everyone for a really interesting Q&A session. And I think I'm going to hand back to Bart now for some closing remarks on the project.
Thank you, Krista. So we have a lot of information on different building blocks for a sustainable growing media. So if you want to know more about these different aspects, we have a video for each of them. We have a fact sheet. We have scientific papers, which are published open access in most cases. And we have the decision tool. So please find this information here. So it will, the presentations will be on the website after the webinar. And there is also a poll that we will launch now to know how informative this webinar was, and if it was what you have expected when you did the registration for this. So from 1, if it's not relevant, up to 5 if it's very relevant. And in the meantime, I can tell you that we have recently launched a new fact sheet. It's about microbiology of these different building blocks. So it's also available on the website. And it was also mentioned for the LCA study, so that we measured the yields of different trials with the peat or the stone wool, but also with the new growing media. And we didn't see big differences in yield, and at least not a yield reduction when going to more sustainable growing media. But the data of these trials, they are also summarized and they are also on the website. So if you can check them there. And so thank you for being in this webinar. So you still can consult everything on the website. You can contact us if you have questions. We are active on Twitter, and we have a lot of videos which are on the YouTube channel of the project. So you can find a lot of information over there. And so I would like to thank you for your for being here in the webinar. And I also would like to thank Cressida for chairing this session, and I give back the word to her.
Thanks, Bart. This is quite a sad event, actually, because we're now coming to the end of the project, and we're really closing down on all the work packages. We've had a pretty crazy ride through the whole COVID experience. We didn't have as many dinners in different cities as we would have liked. But, you know, despite all that, we think we've delivered a pretty successful project, actually, and fingers crossed that biochar can help save the world. So many thanks to Interreg 2Cs for funding the project. And we had some funding, but you'll have to clarify, from some province funding, I think, didn't we, from a couple of regions in Europe?
Yeah, that's we had co-funding in Flanders from the province of Oost-Vlaanderen and the province of Antwerpen. And in the Netherlands, there was also co-funding of the provincie Noord-Holland.
Yes, so and also thanks to all our collaborators, everybody at the different project partners who've been involved with the project in one way or another from start to finish, our observer partners, panelists, people who've attended our webinars, and please stay in touch with us and do access those resources on the website that Bart outlined earlier, because there's some really fantastic stuff there. So yeah, thanks, and hopefully see everybody soon.